Welcome to the second part of the morning session about unsupervised learning, dimension reduction, and data integration. In the first part, we've discussed principal component analysis. And now we will discuss partial least squares. So let's start. First, a bit of background. Recent advances in technology provided many types of biological data sets, so-called omics data or multi-omics data. And here you can see in the figure some examples of omics data. You can see genomics, transcriptomics, proteomics, metabolomics, and so on. So there are different levels of biological variation measured. To extract information from this, there is a need for integrative approaches to combine data and extract information based on multiple data sets rather than one by one. So we typically ask three questions. The first one is, how does variation between omics datasets relate? For example, how much relationship is there? The second is, which types of features induce this variation? For example, which genes are related to which metabolites? And can we benefit from a joint or integrative analysis? So here you can see a figure where the left side represents metabolomics and the right side represents transcriptomics, so gene expression basically. And you can see here metabolite A, B, C, and D, and here you can see, let's say, gene 1 and gene 2. So the question is, by using an integrative approach like this, can we understand which genes are related to which metabolites? So in order to get a better understanding of the biological system. So can we do this? Here you can see that by using this integrative approach, we see that, let's say, this gene is related to metabolite A and B because it's involved in this reaction, and gene 2 is involved in metabolite or is correlated with metabolite A and C and D because it's involved in this reaction. So in general, yes, we can benefit from a joint analysis. However, there's typically high correlation among the features, and the genes are correlated and the metabolites are correlated, and there's also a relation between the features from two data sets. So genes are correlated with metabolites. Therefore, we consider latent variable approaches that can deal with these challenges, where few independent latent variables or few independent components drive the association between, for example, genes and metabolites. To give an example, we consider, again, bivariate data. Suppose we have two genes and two metabolites. We have gene 1 is X1 and gene 2 is X2. For the metabolites, we have Y1 and Y2. Now suppose that the variance of X1 is larger than the variance of X2, and the variance of Y2 is larger than the variance of Y1. Furthermore, let's say that only X2 and Y1 are correlated. So gene 2 is correlated with metabolite 1. Now if we apply Pca to the data matrix X, consisting of X1 and X2, which variables will get high weight? The answer is X1, because it has a higher variance. Similarly, Y2 will get a high weight if you apply Pca to the metabolite dataset. However, when you look at the relation between X and Y, or when you're interested in the relation between X and Y, which variables should get high weight? Here the answer is X2 and Y1. So Pca is not designed to look at the relation between two data sets. It just gives It just gives high weight to variants or to genes that have a high variance within the genetic data, or to metabolites that have a high variance within the metabolite data, and does not look at relations between genes and metabolites. So we need something that actually does look at the relation. There is a method that can do this. It's called partial least squares. So how does PLS work? First, let X and Y be two data matrices. Let's say, for your convenience, gene expression and metabolism. The size, again, we have N samples, and we have P genes, and we have Q metabolites, right? And note that typically P and Q can be very large, or can also be small, depending on the context. So recall that in Pca, we consider directions of maximal variance. However, here we are interested in the covariation between X and Y, and not necessarily in the variation within X or within Y. So we need to do something else. Consider the covariance between X and Y. We can write that as this product, Y transpose X, or in X transpose Y, say. The dimension of this matrix is Q times P, and the number of metabolites times the number of genes. To obtain, again, weights that maximize the covariance between projections of X and Y, we again need a little bit of math. So just as in the Pca case, let's define some weights, W for X and C for Y. Now the objective function is C transpose Y transpose XW. It's basically the covariance between XW and YC. And we maximize this for all C and all W such that, again, the sum of the squares is 1. So the square of the elements sum up to 1. We again do the Lagrange trick, yielding this maximization problem. Find the highest covariance. However, it should satisfy the constraints for W and also the constraints for C. The solution can be obtained in the same way. So you take derivatives with respect to W, and then with respect to C, you set it to 0 and you solve. And again, the solution is a very well-known concept in linear algebra. It's namely the singular value decomposition, as we've seen in Pca. So this means that the best W, so the first component of PLS, is the first right singular vector of Y transpose X. And the best C, so the best set of weights for Y, is the first left singular vector of Y transpose X. So right singular vector because X here is on the right hand side, and left singular vector because Y is on the left hand side. So these weights have almost the same interpretation as Pca, except that these weights indicate importance for the covariation between X and Y, for the relation between X and Y, instead of the variance. The scores can again be calculated by projecting the data onto the weights. So for X, or for the genes, we have T is X times W, and additionally we have now U is Y times C. So we have genetic scores and we have metabolite scores. Again, an example. So this example shows you the difference between Pca and Pls. First of all, we can run Pls by using a package, the OmicsPLS package. This is explained in the exercise. Again, we simulate two genes, gene 1 and gene 2, and two metabolites, metabolite 1 and metabolite 2. So gene 1 is basically 100 points or 100 samples from a normal distribution. And gene 2 is also 100 samples from a normal distribution. However, the standard deviation is slightly lower. So here the standard deviation is 1, and here it's 3/4. The first metabolite is again 100 drawings from a normal distribution. And here the second metabolite is actually equal to the second gene. So the second metabolite and the second gene are correlated, even stronger, they are exactly the same. So very highly correlated, you could say. Okay, so we construct the data matrices X and Y, again by using cbind. And then first we calculate the Pca solution. So Pca, remember, was the right singular vectors of X, the SVD of X, and then the right ones. And the solution is, let's say, minus 0.99 and here minus 0.50. Yeah, so you can see that the first gene gets a very high weight and the second gene gets a low weight. Now if you calculate a Pls Fit, so the first partial least squares component applied to X and Y, and look at these weights, so these weights are now based on the covariance rather than the variance, you can see here the result. So the first gene gets a weight of 0.03 and the second gene gets a weight of almost 1. Yeah. So for Pca, the first gene was very important. For Pls, the second gene is very important. Yeah. So here you can clearly see the difference between Pca and Pls. So Pca looks at the variance. Indeed, gene 1 has a higher variance. And Pls looks at the covariance. And indeed, gene 2 has a higher covariance with the metabolites than gene 1. To summarize, for given datasets X and Y, we want to inspect their relation, so not only within X or within Y, but between X and Y. We consider directions of maximal covariance rather than maximal variance. This direction is represented by weights for each feature, just as for Pca. However, these weights now have the interpretation of being important for the relation between X and Y. And these weights for Pls are calculated by a singular value decomposition of the covariance matrix Y transpose X, or X transpose Y. Again, the projections of the data onto these weights are called scores. And one can again interpret or plot the weights and the scores to understand which features or samples are most important. You can again look at outliers, both outlying genes or outlying samples, or you can look at clusters of correlated genes and samples and look if you can biologically explain that. And so where Pca looks at the variance within X or the variance within Y, Pls is an integrative approach because it looks at the covariance between X and Y. This was the second part of the morning session. Thank you.